Okay. Okay, welcome to the symposium of DIM. This time we have a nice speaker. For the first time, I will say. Daniel Remenik. I will say some few words in English and then I pass to the Spanish, okay? Daniel is a mathematical engineering from this school. And then he got a PhD in applied mathematics at Cornell. I think under the supervision of Duret, no? Okay. Well, he has been working in several areas. One of them is KPC, which I do not understand the name KPC. So I never remember the three mathematicians or physicists behind that. So maybe Daniel will explain that. Daniel is a professor at our department. He's a full professor. Sort of. And he's also a main researcher at the CMM, okay? He has many, many honors and distinctions. He's amazing about that. He has the Frontiers in Science Award this year. Plenary speaker at the International Congress of Mathematical Physics. Wow. Rollo Davidson Prize. My goodness. MCA Prize 2021 is the Mathematical Council of the Americas. And also he was Marcos Orrego Puelma Award at our school to the best student of his generation in mathematical engineering. He has many, many publications and citations and has a long history of collaboration with many people, which I would like to mention some of them. Sorry if there's somebody in the audience that I don't mention. Kestel is one of your, Matetsky, Corbin, Rick Duret, and many others from Europe, United States, and Latin America. And he also has many co-authors in our department. I will say Servet is one of your first co-authors. Ivan Robaport also, Alejandro Mas, they have a very nice paper. You never invite me to that paper, so I'm very, okay. I don't find the word in English for that. Felipe Tovar, also, and Jorge Silva, and so he has many collaborators in the school. One can say that he is his own collaborator. Why not? It's an equivalence relation. And so he will speak about one-dimensional random growth and the KPC fixed point.
Okay. Thank you very much, Jaime, for the nice introduction. Oh, good? Yeah, okay. Yes, okay. So thank you very much for the very nice invitation and for introduction, and the invitation to speak here to the organizers. It's nice to see all of you here. Thanks for being here on maybe not the best day to come for a math talk. But still, so yes, I'm going to talk about this thing that has to do with these three letters, KPZ. But I'm going to start by describing what is one-dimensional random growth, or the sort of one-dimensional random growth models that I want to look at. Okay, so what is going to be a bit strange because I cannot see it there, so I have to look at it there to see what I'm talking about, but still. So what is one-dimensional random growth? For me, a one-dimensional random growth model is going to be a one-dimensional height function. So think of it as some sort of interface evolving in time, and it's evolving as a Markov process. Okay, so it's a Markovian process. The state space is a space of functions from either the reals or the integers to the reals evolving in time. So here's one example of the sort of model that I would like to analyze, but we don't know how, but it's still a good introduction, which is something called ballistic deposition. So this is a model happening on the integers, and you have these boxes falling from the sky at rate 1. So at every site, you have a +1 process of rate 1. And then these boxes fall, and they just sort of stack on top of each other, but they stick to the sides. So if you have something like that one, it sticks there, and it just gets stuck. And that's what you see. So here's a simulation. Okay, and it looks like that. It looks a little bit like as if you were playing Tetris and you're not very good at Tetris. Yeah, okay, so this is called ballistic deposition, and here's that's I mean, that simulation I got from YouTube. This is a simulation I did. It's not so hard, and this is a simulation of ballistic deposition. And the sort of thing we want to study is this interface. Okay, so you can define some interface between the occupied region and the unoccupied region. In this case, you have to make some choice, and you have this interface, and we want to try to understand how this sort of interface evolves. One thing you may sort of believe, and it's pretty clear, and it's not so hard to prove, is that this interface sort of macroscopically is growing linearly in time. Okay, if you don't really worry about fluctuations, it's sort of evolving at some speed and growing up. Okay, so yeah, this is a nice. Okay, this is like ballistic deposition in real life, if you want. So this is a windshield, and it's very cold, so it's frozen on the bottom. And it's raining, so you have these drops coming down, and when they come down, they touch the interface and they stick. They get frozen and they stick. Okay, so this is really like ballistic deposition. Anyway, okay, so we really don't know how to say essentially anything but conjectures about this model. Okay, but it's the sort of model you can have in mind. Okay, so now I come to the K, the P, and the Z. So that's Cardar, Parisi, and Zhang. They are actually three physicists. Parisi is the famous Parisi that won the Nobel Prize 2 years ago or something like that. Not really for this, but he has done a lot of things. And the KPZ equation is, you can think of it as a possible sort of canonical model for random growth. Okay, it's a complicated model because it's a stochastic PDE, so it's like an SDE if you have seen these things already, but it's actually a stochastic PDE. So these PDEs in general are complicated. But anyway, so what you have is, so there's this H, which is this height function. This is the interface that's evolving in time. Okay, and if you, okay, so on the left-hand side, you have DTH, so that's just the rate at which H is evolving. And then on the right-hand side, you have three components. So the first component, let's first look at that. That's just a second derivative. It's a Laplacian. Okay, and what it's doing, it's that it's basically, if I only had dTh equals dx squared h, that's the heat equation. So this is the smoothing part. It just smoothes things out like the heat equation. Now there's an additional lateral growth term, which in this case, it's chosen to be dx h squared. So you take the slope and you square it. And so when you have something, this is what I'm trying to represent here. If you have something that's sort of steep, it's sort of going to grow outwards. And you can see that, let me go back. You can see that more or less clearly here. You have this sort of lateral growth in the ballistic deposition. So one way to try to model it in a continuous model would be like that, yeah, with this lateral growth. And then there's a space-time white noise. Let's not worry about what space-time white noise is, but it's if you want, a sort of two-dimensional Brownian term happening there. Okay, and that's driving the evolution. Okay, so this is where this is called the KPZ equation, and it was the first model of this type in a way. It was introduced by these three physicists in a very famous paper in 1986, and it's supposed to describe a huge class of models describing random interface growth. So here's what the physicist predicted, actually even before KP and Z. So even from the mid-70s, this is completely non-rigorous. So what they say is the following. So number one, okay, you can imagine that there's this linear growth. So this is a piece of paper. That's another example. You have a piece of paper that's burning, and you have this front going down. So you may expect this to advance linearly in time. So there's this speed. But then the question we want to ask is, how does it fluctuate? So if I look at a certain position, how does it fluctuate away from this sort of law of large numbers, if you want to think about it? A little bit like a central limit theorem, but that's one question. And what physicists predicted is that this fluctuation should be of order t to the 1/3, okay? Which is different from what you would expect in a Gaussian case, which is usually t to the 1/2. Although here it would be a little bit of a lie to say t. Here it would have to be t to the 1/4 actually, but let's not get into that. It's still anomalous and it's t to the 1/3. And then the other question you may ask is, at which scale do I see something interesting spatially? So one way to think about it is, okay, if I look at this position and that position, and I run this for a long time, at what distance do I have to look so that I see something that's non-trivial? So if I choose 2 points that are sort of very close together, then the height is going to be essentially the same. So I don't see something interesting. If I pick 2 points which are very far apart, then they're going to be more or less independent. And again, it's not very interesting. So what is the right scale? Okay. And by essentially doing something which corresponds to renormalization group analysis, which is something that physicists like to do in this business, but it's completely non-rigorous, they made this prediction of an exponent t to 1/3 and t to the 2/3. So mathematically, one way to try to study something like that would be to do more or less what one does if you have seen the scaling of a random walk to a Brownian motion. I take my random walk and I can rescale it so that I get a Brownian motion. So here what it would mean is that I take my height function, I subtract this linear growth. So that's like subtracting the mean. Okay, so now this thing has, think of it as mean 0. And then what I want to do is I want to divide by t to the 1/3 because the conjecture is that the fluctuations are of order t to the 1/3. So I divide by t to the 1/3 and see what I get in the limit. Okay, and if I want to see a spatial process, then I don't have to look at x, but I have to look at x at this scale. Okay, so I want to sort of look at x's which are at that distance. Okay, and take the limit and try to see if I can say something when that goes to infinity. Okay, so this is called the KPZ scaling. And the KPZ, that's, yes. So this is called the KPZ scaling or the 1, 2, 3 scaling because it's it's that 1 of the minus 1/3, which is the size of the fluctuation, the 2, which is the spatial parameter, and then the 3/3 in that t, that's the 3. So it's 1, 2, 3 is the relation between the exponents with time, space. I said it backwards, but time, space, and the size of the fluctuations. And so actually the sort of thing that I want to look at is not exactly this. I'm going to do something slightly different. So if I take t to infinity here, then I lose track of time because I sent time to infinity. So another way to try to keep track of things is I'm going to keep t and I'm going to introduce a new parameter epsilon, and now I'm going to think of epsilon as going to 0. I'm going to send epsilon to 0, but you should think of epsilon to the half as playing the role of t to the 1/3. So when t goes to 0, this becomes small, which is the same as epsilon to the half becoming small, and then I'm just copying all that. So this is, if you want, I was going to say it's a technicality. It's not really a technicality, but when I do this, I can sort of still keep track of macroscopic time. I take epsilon to 0, and I still have this t. And after I take epsilon to 0, if I can say something about this, I still have t in my picture, and I can see how these things evolve in time. Okay. Anyway, so here's one more video. So this is again something that's supposed to look a little bit like the KPZ equation. And this is a real video. Actually, I was worried that it was fake the first time I saw it, but actually it's not fake. So this is a park in Spain, and there's this sort of, I'm going to say it in Spanish, but está como una pelusa. I don't know how to say it it's pop art fluff in the ground, and then somebody set this thing on fire for some reason, but this fluff burns very quickly, so it just burns, and there's no time for the grass to get on fire, so you have this front advancing, and it looks nice. I mean, and this is sort of expanding in this KPZ type way. I mean, it looks nice because all I mean is that the grass is not burning. Anyway, okay. So there's many other examples. I won't go into this in detail. So let me just mention this one. So okay, other examples of models which are in this class. So for now, I have looked at just random interface growth, but here's one example of something which in particular looks in principle a little bit different, which is traffic models. So here I'm just thinking that I have a street, okay, and I have cars, and my cars try to jump to the right at rate 1. So that's like they drive at some sort of random speed. But if you have a car in front, you can't cross. Okay, so for instance, if this one wants to jump, it jumps. But if this one wants to jump, it has to wait until the car in front moves. And then what you can do is you can associate a certain interface function by basically counting how many, more or less, counting how many cars you see to the right. So every time you see a car cross, you're gonna have one more car to the right, and then the interface goes up at that position. Okay, and if you do that, you get an interface growing in time, and then the conjecture, and this is a famous particle system called TASEP. The conjecture is that this should also sort of belong to the same class. It should also have t to the 1/3 fluctuations, and the structure should be t to the 2/3. Okay, and there's other things which I put here. So it's a very wide class of models. Some of them are mathematical models, which we can sort of describe mathematically. Some are just physics or biology, and where the conjecture is that they should share the same sort of behavior. Okay, so let me tell you what is the actual behavior that I'm conjecturing, if you want. So the conjecture is the following. The conjecture is that if I take any model in this class, I haven't said what the class is, any model in this sort of vague class that physicists say should exist. So for any model in the class, there's something corresponding to this height evolving in time. And then if I rescale it in the way that I told you, so I put these epsilons in front of t and x and in front of the fluctuations, and I send epsilon to 0, then I should get a limit. And this limit should always be the same. Okay, so there's a unique universal limit, which is called the KPZ fixed point. And this limit should arise for every model in the class. So you can think of this as the central limit theorem. If you sum independent random variables, it doesn't matter what you're summing, as long as they satisfy something, they go to a Gaussian. And then you can try to relax this, and you can try to extend it a little bit more, and so on. So that's the sort of thing I'm saying here. So if there's a model that's in the class, then if I rescale it like this, it's gonna go to some limit, and I'm not telling you yet who's this limit. So this limit is supposed to be universal in that sense, just like the Gaussian is universal. It arises for all models in this class. There's some constants that I have to finely tune, and those are not supposed to be universal. Just like in the central limit theorem, you have to subtract the mean, say, and then the mean, well, it depends on the model. But after you subtract the mean and after you normalize, you get a normal 0, 1. Okay, so these constants are not universal, but the rest is. And this thing, as I was saying, it's called the KPZ equation. The KPZ fixed point. It's not the same thing as the KPZ equation. And part of the conjecture is that the KPZ equation itself should converge to this KPZ fixed point. Why is it called the KPZ fixed point? It's called the KPZ fixed point because it's invariant in distribution under this rescaling. So it means that if I take I have my process, and now I rescale it in the same way. I fix alpha, and I put this 1, 2, 3 scaling inside, I get the same process in distribution. So you should think of it as I renormalize, I rescale by alpha, and I get under the scaling, and I get the same process in distribution. If this limit exists, then this is completely straightforward. It just follows from the fact that I'm taking a limit with this 1, 2, 3 scaling. So just by multiplying epsilon by alpha or by alpha squared or something like that, you get this identity. So it's part of the definition. And this is, for those of you who know Brownian motion, this is the analog of saying that Brownian motion is invariant under diffusive scaling. So if you put an alpha in front and you take time and you divide by alpha squared, then that's again a Brownian motion. It's the same sort of thing. Now, there's one thing I haven't said yet, which is that the limit is universal, but it actually, the conjecture, and this is true actually, it depends on the initial condition. So even though this is universal, it depends on how you start, what you're gonna see in the limit. So here's a simulation again. So this is actually the same picture that I was showing before, where you're starting from what I would call a flat initial condition. So you have these boxes falling from the sky, and you see this, okay? And if I now start something slightly different, where you should think of this as I started from one box, and then if I have boxes falling on the sides, they just go to -infinity. But eventually I have a box that sticks to the side, and now I have a slightly bigger box, and then this thing starts growing outwards. Then you already see that this can't, at least from far away, it doesn't look the same as that because this is sort of flat. It's sort of macroscopically flat, but this one is curved. Okay, and actually you see that in the limit. So that's the conjecture. There's a unique limit. It's invariant in distribution, but it depends on the initial condition. Okay, so that's so I want to see how much time I have used. Okay, so this is sort of the broad picture to try to have in mind. Okay, and this is completely vague, so don't try to make it to understand it as something precise. But actually, let me go back for a moment. I was saying that the conjecture is that any model in the class should converge to this thing that I'm calling the KPZ fixed point. But actually, I can turn that definition, that conjecture around, and I can say, well, this is not a conjecture, this is a definition. So now I'm gonna define the KPZ universality class. I'm gonna say the KPZ universality class is the space of models that converge to this thing. And if I know what that thing is, then I have really defined the KPZ universality class. Okay, so that's like saying the Gaussian universality class is the space of models such that when I rescale them correctly, I have a central limit theorem. Okay. Okay, so the conjectural picture is the following. The conjectural picture is that there's a, you should think of it like this. There's a space of models, and then there's this fixed point of this renormalization, this operation of rescaling in this 1, 2, 3 way. And there's a unique fixed point, supposedly, and this fixed point is the KPZ fixed point. So you can think of it as some sort of abstract dynamical system, and all these models are going to this KPZ fixed point. Okay, and this is telling us who the class is. And then there's some other fixed points, and there's some of the models that I have. So there's KPZ equation here, which is special. There's this is the one with the cars that I was describing before. There's ballistic deposition. And there's another one, which is the one that I'm going to introduce in a moment. Okay, but the conjecture is that they all go to this KPZ fixed point. And actually, I'm already giving away a little bit of what I'm going to say. So we know this for some models. So the ones here where I put these lines, we know. And the ones over there, we don't know. Okay. In particular, we know nothing about ballistic deposition. Okay, so this is the broad picture to try to have in mind. And so what I want to do in the rest of the talk is to tell you who is this guy, more or less where it comes from, and some properties. Okay. Okay, so let me go back here. If you want to, I want to go back to the analogy with the central limit theorem. Suppose you have the idea that there should be this Gaussian universality class, but you know nothing about who should be the limit. You don't know that the normal exists. So one thing you may do is you just throw coins and count. Okay, what is the distribution of the number of heads that I have after many times? And then I can, well, when I get a distribution, it's not so hard. It's actually a binomial, and then I can compute the limit explicitly. And I will see the Gaussian. Okay, actually, that's one way to prove the very first central limit theorem. I'm going to see a Gaussian, and then now I have a Gaussian, and with this Gaussian, I could define the Gaussian universality class, and then I can start playing the game of trying to prove that other things go to the Gaussian. So I'm going to play that game here, but I have to choose one model. So if I want to tell you that's a strategy. If I want to identify who's that, then I'm going to choose one model. I'm going to try to choose a model that's simple or simple enough so that I can say something. Of course, this is more complicated than throwing coins. So the one I'm going to choose is this one in this case, because I want to, I mean, there's some nice things about it. It's something called the polynuclear growth model. So I'm going to introduce it next and tell you some things. Okay, so here's now I'm going to define I'm going to explicitly define a model, which is the one I'm going to use, which is called this polynuclear growth model. Okay, and I'm going to say P and G because the other name is too long. So again, I have a height function. So this height function, it lives on the real line, but the heights are integers. Okay, and it looks like this. So every time you see I mean, it looks like a piecewise constant function. And the way it evolves is the following. Okay, so you have these sort of constant islands, and they expand out at speed 1. So there's three parts of these dynamics. So the first part is that these islands expand out at speed 1. And that's completely deterministic. Because you run it, they're just expanding out. Now at some point you may have two of these islands getting close together. Well, when they collide, they just merge and nothing happens. Then you have just one island. Okay. In both directions. No, you have the one on the right is doing this, the one on the left is doing that, and when they collide, it's now a wider island and it's expanding out. Okay, I'm going to show a simulation. Maybe I can show you already the simulation, but it looks like that. Okay, there's a triangle here that I have to explain in a moment. Okay, but that's how it looks. So now let me go back for a moment. Okay, and then there's the only random part is what I'm calling nucleations with intensity 2. So technically what you have is a space-time Poisson process of rate 2, but don't worry about that. So essentially what you have is that homogeneously everywhere at a sort of Poisson point process at every site, though it's not really sites, this is a real line, but that is a technicality, you have a nucleation. So you have a single island of width 0 popping up on top, and then it starts spreading. Okay, so every now and then you have a single island, and then it starts spreading. So this was introduced by Gates and Westcott, I guess like 30 years ago as a model of crystal growth. You should think of this as sort of crystals growing on top of each other. I mean, layers of a crystal growing. Here's a simulation again, and maybe this simulation is better. You can see now the movie. Okay, so you can see, okay, it's these dots here, I'll explain this in a moment, but these dots here are the space-time Poisson process. So you have this line going up, and every time the line touches a blue point, you have a nucleation on top and it starts spreading, and this is what you see. Okay? And this is how it looks. I think it will start again. Okay, so one more thing to say here is that I am choosing one initial condition, and it's not the same as the initial condition in that simulation. So in this simulation, the initial condition is flat. So you have a flat interface, and then you have these things popping up everywhere. Here I'm using a different initial condition where I imagine that there's a single, it's a little bit like what I was showing you with the ballistic deposition. So there's a single site here, which has, at the beginning of time, it has height 0, and then there's nothing here. So you have a single seed, and it starts expanding. And then on top of that, you have these nucleations, and this is what you see. So that's why I don't care about what happens over here, because if I have a nucleation here, it falls over -infinity, and I don't see it. Okay, but if you want to think of it more simply, you have this again. This seed, it's going out, it's expanding like that, and then you have this random thing on top, and this is what you see. And the conjecture is that this thing is a KPZ-like interface evolving in time. Is the model clear? You don't need to get the details. It's just okay. So this is the initial condition. This initial condition is called droplet or narrow wedge. So droplet because you think of you have a single droplet that's expanding. It's also called narrow wedge because there's a wedge, and then when you scale it, it becomes a narrow wedge. But don't worry. So here's one way to represent it. Okay, so this is really like a snapshot, if you want, of the picture. So I have these dots. These are the nucleations, and at every dot, I have these islands sort of going out. And when I have two of these islands colliding, like happens here, they merge. Okay. So actually, you can draw this. You can really draw this picture. And if you want to not know what is the height function at this time, so here I did it. So if I want to know, say, this height, all you have to do is count how many of these lines I cross. Okay? So a different way to say this is if I want to know what is the height over there at the origin here, I just chose the origin, what you have to do is the following. You look at the points you have inside, and you have to look at all possible ways in which I can go. So I want to look at a path that goes like this. So it's like, it only uses angles between -45 and +45 degrees. or if you want, it's a Lipschitz function with Lipschitz constant less than 1. It goes like that. And I want to go from this point to that point, and I want to eat as many cookies as I can. Okay, so in this case, it's 4. And then 4 is exactly the height over there. Okay, so that's one way to realize the process in this case. And actually, there's something nice about this, which is that, oops. Yeah. So now, if you turn your head like 45 degrees, this configuration of points defines a random permutation. It's very simple how you do it. So you just look at the points in this order compared to that order. So for instance, this is the first point in that order, and it's the second point in that order. In the eta direction, this is the first one, but it's the second one in the zeta direction. So in my permutation, it means I send 1 to 2, and then I send 2 to, I guess, 3, and then I send 3 to 5 or something like that. Okay, so I have a random permutation. And this length is exactly the length of the longest increasing subsequence in this random permutation. So you look at your permutation here is like something like, I don't know, 2, 5, 4, 3, 6. You look at all possible subsequences, and there's one, or there's more than one, but there's a maximal length of that subsequence. And that's exactly what this path is doing. Okay? So actually, okay, there's a random number of points inside, but just fix the number of points. Suppose that it's deterministic or conditional on the number of points. In this case, it's, I don't know, 6, I think. And what you're doing is you're choosing a random permutation. And this is a very old problem, or relatively old problem in combinatorics, that some people here know. It was a famous problem first to say, okay, if I have a random permutation of size n, what is the length of the longest increasing subsequence? And it's not very hard to prove that it grows like square root of n. Okay, so if you take Ln, which is this length, you divide by square root of n, then that converges to a constant. That's not a very hard theorem. So there was an open problem for, I don't know, maybe 20 years, 15 years, I don't know, of computing that constant. Maybe there's a typo, maybe it should be square root of 2, I don't know. Maybe the 2 is inside, I don't remember, but it's something like that, so it can be computed. And then at the end of the last century, Bike, Dijk, and Johansson proved a very famous theorem where they showed that not only, okay, this was known already, but it turns out that if you now look at the fluctuations of this length about this 2 root n, so this is like the law of large numbers, then the fluctuations are of order n to the 1/6. And if you divide by n to the 1/6, you get a famous random variable. And this random variable has to do with something completely different, which is random matrix theory. Something called what is the longest increasing subsequence of a uniformly chosen random permutation. I should have said it. Okay? So you take a random permutation of, you take an alphabet of n letters, you take a uniformly chosen among the n factorial possible permutations, you take one uniformly chosen, you look at the longest increasing subsequence, you subtract that, you divide by n to the 1/6, and you get something called the Tracy-Widom GUE distribution. And what is this? So very quickly, so in principle, it looks like it has nothing to do with anything. So what you do is you take a random matrix, you take a matrix, you fill it in with Gaussians. Actually, it has to be complex Gaussians, but all that means is that it's real part plus, a Gaussian real part plus an independent imaginary part. And then, well, there has to be some scaling, don't worry about that. And you condition it to be Hermitian. Okay, so it actually means that you only pick things on top of the diagonal, and then below you have to transpose and conjugate. So this is a matrix. It has it's an Hermitian matrix, so all the eigenvalues are real. You look at the largest one, and that one satisfies. That one has fluctuations given by this Tracy-Widom GUE distribution. Okay, so what I'm trying to say is that the fluctuations of the longest increasing subsequence have the same distribution as the fluctuations of the largest eigenvalue of a random matrix, of a specific random matrix. And what this tells us, so remember that my Ln is the same thing as the height of my interface. So it really tells me that if I look at this PNG thing, then, yeah, okay, here. It tells me that if I look at my PNG thing, then if I subtract 2t, at least if I look at 0, and I divide by t to the 1/3, this goes to the Tracy-Widom GUI distribution, to this random matrix distribution, okay, which is, well, it's surprising. It might be surprising. I still find it surprising. Okay, this is the, forgetting about this. This is the scaling that I wanted. Right? I take my height function, I subtract the law of large numbers, and then I divide by t to the 1/3, and I get something meaningful. So the fluctuations are really of this order, t to the 1/3, and I get this random matrix thing. Okay, so this is the, if you want, this is the beginning of the story, and then people could do the following two cases. So one, the first thing that people could do, this is still sort of early at the beginning of the century. Instead of just setting this to be 0, I can actually put this t to the 2/3 that I had put before, and I can describe the whole process. So now it's not only at one point, but the whole spatial process, and you get something called the area 2 process minus a parabola. So the parabola is, I don't know if you can see my pointer, but that's the parabola. It's basically the parabola you're seeing. And then on top of this parabola, there's some fluctuations, and it's something called the area 2 process, which sees this random matrix distribution at every site. Okay, and then the next case, which was solved, is the case of the other ones that I have been showing you, which is the flat initial condition. So now I start here flat. I start doing this. I see what I see on the bottom, on the top. I'm sorry, and I get something called the area 1 process. Don't worry, those are just names. But actually, there's again a random matrix distribution here. So if I look at the fluctuations, they're not the same as those ones. These were called Tracy-Widom GUI. These are called Tracy-Widom GOE, and it's basically the same story, but now it's Gauss. Again, it's Gaussian matrices, but now they're real and symmetric instead of being complex and Hermitian. And that's a theorem from, well, depending how you count, but either Bike and Reins from 2001 or the full case, it's from 2008. Okay, so the question I want to ask is, what if I do a general initial condition? Because remember that if I want to characterize this thing in general, I have to do it for a general initial condition. I have only done it for 2 special initial conditions. Okay, so that's the question that I want to answer. So here is the answer. So at least stated in the context of this PNG process. So this is a theorem with 2 of the names that Jaime mentioned, Konstantin Matetsky and Jeremy Questel. And the theorem is the following. The theorem is, if you have PNG, so you take this process, you rescale it in the way that I told you. Okay, so you take the height function, you have this 1, 2, 3. Okay, there's some constants, these 2s, but those are not universal. I just have to fix them in some way, and I have to add this because that's the linear thing. And I take a limit, then actually that limit exists, and it defines a Markov process in a space of continuous functions. Actually, it's not continuous functions. It's a space of upper semi-continuous functions. Okay, so it does define this evolution, this macroscopic evolution. So I actually know all the limits, and I can sort of keep track of how the thing evolves in time because it's a Markov process. So being a Markov process, I have defined it for all times. What else do I want to say? Yeah, so how is it defined? It's defined by given what's called the finite dimensional distributions. What I can tell you, there's an explicit formula that tells you if I want to know what is the height at time t at a bunch of different points. Okay, so what is the probability that at time t and x1, x2, x3, I'm less than r1, r2, and r3? It's given by something called a Fredholm determinant. Okay, so this is like an infinite dimensional version of the determinant. And it's explicit. I'm going to tell you more or less briefly what that is. And it's actually, so it's going to look very complicated probably, but it's not so bad. You can prove things using it. So several things can be proved. One of the things you can prove, for instance, is that this limit looks locally like a Brownian motion. It has the regularity of Brownian motion in space. So it's Holder 1/2 minus in space. And in time, if you fix a point and see how how rough it is in time, it's older 1/3 minus. And the reason, I mean, these 2 and these 3 come from the relation, this 1, 2, 3 relation. Okay, there's other things one can prove. Actually, this was not first constructed here. It was first constructed as a limit of this system of cars moving randomly on this thing called Texas. But I'm describing it in the context of PNG. Okay, so that's the theorem. So this theorem says the limit exists. I can describe it nicely. It's a Markov process. And now I can say, well, this is the thing that defines the KPZ universality class. And then there's the challenge of trying to prove it for other models. Okay, so here's a non-exhaustive list of what's known now. So I won't even get into these definitions, but now this KPZ fixed point limit is known for a bunch of models. Okay, but not really much more than that. So it's like maybe 10 different models or something like that. And there's a couple of ways to prove it. There's actually another approach, different from what I'm going to show, that it's also now known. So it's now known that this is the same limit for some interesting models, but these are all special models, and we don't know how to do it in general at all. So there's nothing yet like the central limit theorem. So in particular, if I take something like this ballistic deposition model that I showed you, nobody knows how to do anything for now. Okay, so let me show you. This is maybe this is my slide with formulas. Let me try to give you an idea of what goes inside. Okay. So I'm gonna very briefly describe this KPZ fixed point formula in the case of 1 point. So remember, I told you I can look at the height at different points, but I'm gonna just state it for 1 point because it's a little bit simpler. The formula in general is not very different. And the way it works is the following. So the probability that this thing at time t is less than r is given by the determinant of the identity minus, think of it as an infinite matrix. It's really an integral operator acting in L2. Okay, so this is an integral operator, and I have to tell you, if it's an integral operator, I have to tell you what's the kernel of the integral operator. So here's the kernel. And the kernel is, just to say that what is the most important part, okay, it works as follows. So the KPZ fixed point has an initial condition, H0, okay? And I'm gonna do the following problem. I'm gonna put my H0 in space, and then I'm gonna take a Brownian motion. Okay, I'm gonna fix an L, which I'm gonna send to infinity later, and I'm gonna take a Brownian motion, and I'm gonna ask the following question: what is the probability that my Brownian motion goes from eta to c? And so that's simple. That question, the answer to that is just a heat kernel. So that's just the transition density of a Brownian motion. But I want to ask, what is the probability that it does that and it crosses the initial condition of the KPZ fixed point? Okay. So you take that. I call that this heat probability. And now what I do in a way which, let's not get into the details, I want to send L to infinity. So it's a little bit like the following. It's like I start a Brownian motion at minus infinity, and I throw it all the way to plus infinity, and I ask, what is the probability that it crosses the function? Okay, let me say it in a different way. You can think of this in terms of the heat equation. So in terms of the heat equation, you're doing the following. You're solving the heat equation with just delta initial condition, and you go from minus L from time minus L to time L, but it's the heat equation with Dirichlet boundary conditions below H0. So you look at the solution to that, and now you send L to infinity. That makes no sense. You cannot do that. That doesn't converge. Okay, but then you do some things here. Okay. In particular, so the important part, so this is like a heat kernel going from time minus L to L, and then you sort of you apply the inverse heat kernel. Again, that doesn't make sense because heat kernel is not invertible. But the important part is that you now convolve with this semi-group associated to third derivative, which regularizes things, and then you can check that things are nice and everything works. But don't worry about this, but the point is you can take L to infinity, and you can define this thing. So basically what you're defining is a function which tells you what is the probability in this strange way that a Brownian motion comes from minus infinity, exits at plus infinity, and it goes below my function. And then the statement is that you put that inside your determinant, you compute it, and you get the probability for this KPZ fixed point. So here's a corollary if you don't like probability, but this is not a corollary about probability if you want. So if this is the corollary, if you give me this K, then I can tell you who was the function. It's like an inverse problem. In my limit, yeah, I said I didn't want to. Yeah, it's not in the notation. So R actually appears, this should be U plus R, V plus R. That's where it is. It appears, it's a typo. It's not in the, but it just shifts the spatial variables. It's like a shift in space. Okay, but the corollary that I want to say is that this is like an inverse problem. Right. So if I don't know who's H0, but I give you this probability of coming from minus infinity going to plus infinity and going below the function, I can tell you who's the function. And it just follows from this by taking t to 0 in this form. Okay, so that's a consequence of the construction. Okay, so the way one gets something like that is that actually for PNG, and I won't get into any details at all, but for PNG, there's a similar formula. So the KPZ fixed point, I don't know what to do, but I have this limit. But actually PNG, I have a well-defined dynamics, and it's sort of a magic dynamics in a certain way. And there's some techniques that allow you to try to deduce formulas for this. And actually the formula you get is a formula which looks very much in the same way. So instead of having a Brownian motion hitting a certain initial condition, you have a certain random walk hitting an initial condition. And then there's all these things on the sides, but everything is explicit except for the fact that your random walk is hitting a function. But now you take a scaling limit, and the random walks converge to Brownian motions, and then my initial condition converges to the limiting initial condition, so I get this problem that I was saying about the Brownian motion hitting an initial condition. And then there's things on the sides, and yeah, it works. And actually, it's not very easy to, I mean, it's not at all easy to try to guess that such a formula would work. But actually, once you know that what the formula is, you can check it. Okay, it's not a one-page proof. It's a little bit long, but you can check it directly by checking, if you remember your Markov process course, just by checking the Kolmogorov backward equation. You just check by hand that this satisfies what it has to satisfy, and it can be done. Anyway, so that's, I haven't really said anything about the proof, but that's basically the proof. You construct something like this, you take limits, and then you get the formula that I was showing you before. Okay, so okay, I have a couple more slides, but not too much more. So then comes a connection with something called integral systems, which it's not going to be familiar to most of you. But let me point something out, and maybe this picture explains it. So, so there's something very special that happened, because I have this complicated evolution, this KPZ fixed point, which I don't really, it's complicated. I just try to compute the limit. I can't say too much about it, but the distribution, in this case, the one-point distribution is given by the determinant of the identity minus a kernel. But the kernel, even though it looks complicated, it has all these infinite Brownian motion going from, the dependence on the parameters is linear. It's really linear. It's very simple. Maybe if I go back, so this is the definition. It's not easy to parse, but imagine the only thing that depends on t here is the kernel. And if I differentiate this in t, there's t here and t there. And if you interpret correctly, all it means is that you have third derivative on one side and third derivative on the other side. And that's a linear equation. So that's the equation I wrote here. The derivative in t is just a sum of spatial derivatives in the arguments. In x is the same thing, but you get second derivative. And in R, which is what Jaime was asking, it's also linear. So everything is linear. So something strange happens here. I mean, okay, maybe it's not strange, but it's nice. So you have this complicated evolution at the level of this KPZ fixed point. But when you go back to the formula, the evolution of the kernel is very simple. It's just linear. So I can think of it as working as follows. If I want to know what are the transition probabilities of this KPZ fixed point, instead of computing the transition probabilities directly, what I can do is I can think that I evolve my kernel linearly, and then I apply, and then the evolution is simple, it's linear, and then I map it down through the Fredholm determinant, and I get my evolution. So this is like the hallmark of an integral system. There's a certain there's a big simplification. Integral in this case means that not integral in the sense of being in L1. It's integral in the sense of that you have explicit formulas for it. And the reason there's explicit formulas is that this complicated, in the sense of, yeah, it's exactly, it comes from mechanics. It's in the sense that, but in this case, it's in the sense that there's a way to simplify, like I go up in the clouds and I evolve this thing linearly and I get something, a simple evolution, and then I map it back and I do what I want. So it's hard to, this is hard to describe how it evolves. But up there, this is not something physical. This is just the kernel that appears in the formula, but that's linear. So okay, this you have seen again inverse problems and sort of inverse problems for like the scattering problem for KDB and stuff like that. It's sort of a similar sort of thing. But you can get something out of this. And it really, so what I'm going to show now, it really follows basically from this and several pages of computation. So here's the theorem. So do the following thing. I mean, the idea is the following. I have this linear evolution and it's simple. So maybe I can say, since I have this linear evolution on the kernels, maybe I can say something about how the Fredholm determinant evolves as a function of t, x, and r. And here's the statement. So I'm going to give a name to this distribution function. Again, I'm doing it only for one point because it's simpler. So I take the probability that h is less than h at, okay, here. At time t, I look at my height function. What is the probability that at x is below r? I call that f. Remember that this thing is the limit of my microscopic thing. Okay? And then I take the logarithm of that and I take two derivatives in r. And I call that phi. So that's the second logarithmic derivative of f. So this is something usual. Actually, you can understand where this comes from. So this is something usually in integral systems, but I have a determinant. So a determinant is not linear. But if I differentiate a determinant, I get a determinant times a trace. And if I take the log, then I get the determinants cancel and I only get a trace and now I have something linear. Okay, so that it sort of linearizes the problem. It's still not really linear because I get a nonlinear equation, but the equation I get is something called the KP equation, the Kadomtsev-Petviashvili equation. And here it is. So this phi solves this KP equation. This is a famous equation in fluid dynamics, I guess. It's a two-dimensional extension of the KdV equation, of the Korteweg-de Vries equation. Okay? So the Korteweg-de Vries equation is the equation that describes how waves move in shallow water. It's very famous. Also, there's people here who know much more than me about it. And the KP equation is a version of this equation where you add one spatial variable in a certain way. And yeah, you have this equation. Okay. In particular, if you start the KPZ fixed point with flat initial condition, so since it's flat, and since the dynamics is translation invariant, it doesn't, I mean, everything does the same at every site. So you can convince yourself that this distribution doesn't depend on x because the initial condition is the same everywhere. So this doesn't depend on x, f doesn't depend on x, so phi doesn't depend on x. So this x, this part here drops. Okay, you can drop also this, and you get this, and this is the KdV equation. In the flat initial condition, this thing actually satisfies the KdV equation. And this is basically my last slide. There's no real connection that we know of, or nobody has told us, no physicist about, probably there is just no connection between this random growth evolution and this KP equation physically. It just appears, okay? But it does have a nice consequence, which is that this gives you at least one way of explaining where these random matrix distributions come from, okay? So again, very briefly, but basically, think about the flat case, okay? So in the flat case, the initial condition is flat, so it doesn't depend on x. And it's also scaling invariant under this 1, 2, 3 scaling. Because if I take the function 0 and I scale space and then I multiply by something, it's still 0. Okay, so the initial condition is scaling invariant, the evolution is scaling invariant. So that tells me that the f that I see at a later time, if I start with flat initial condition, it's the same in distribution. Okay, so if you try to parse what I just said, it means that what you want to do is, well, this is a bad choice because I did it for the step initial condition, but basically what it means is that you can, this phi in this special case, it stops depending on t, x, and r. It just depends on a single variable, just by scaling invariance. Okay, so this phi now can be written in terms of a single c depending on all the variables, but inside there's only one variable. And if you now put this phi inside the equation, you can map it to something called the pi-Levet-2 equation. And this is what gives you these equations. What they say, if you go back to random matrix theory literature, it tells you that what you're seeing is these random matrix distributions. So to try to say it more concisely, just from the fact that this distribution is solving these special equations, and in these special initial conditions that have this connection with random matrices, the fact that they are scaling invariant, just out of that, you get these Tracy-Widom distributions, these random matrix distributions. So in a way, that gives at least one physical explanation of where they come from. Okay, so I'm not even gonna discuss this, but let me, in the case of PNG, there's also equations of this type. Okay, it's something called the Tora equations. It's like a discrete version of these KP equations, and it works in exactly the same way. It's rather complicated, but there's also equations. And yeah, I'm gonna stop there. So thanks for listening. Thank you, Daniel.
Thank you. We have time for some questions. People in the Zoom can ask by writing us a question in the chat, please. Abelius.
So for PNG, is there any meaning in the two that you choose for the Poisson point process intensity? And furthermore, what happens if you do it randomly? If you put a randomness on the intensity of the Poisson point process?
Yeah. So the two, there's no meaning. It's just a choice. It's just the standard choice in the literature. So we do it. If you change it to say 4, then things would run twice as fast. Then it would have to change constants everywhere. Okay. I just used, maybe I should have put 1, not to make it confusing. It's just the standard choice. Yeah, it just changes the scaling. Now, the next question was, what if I, instead of putting an homogeneous space-time Poisson process, I put something inhomogeneous? I make it depend on time, or I make it depend on space, and it doesn't have to be exactly homogeneous. Okay, so maybe there's sites where I'm trying to explain your question. There's sites, there's regions where I have more nucleations and regions where I have less nucleations. So that's a very good question, which I would love to know the answer to. So the basic answer is that all these special computations break down in that case, except for some little things. And yeah, it's sort of the sort of thing we would like to do, and maybe there's some chance. But it's a good question to which we don't have an answer.
Is it expected to be in the universality class?
So actually, so again, it should be in the universality class, but maybe the limit is not the KPZ fixed point; it's some sort of inhomogeneous KPZ fixed point. So there could be some sort of KPZ fixed point where the evolution is a little bit inhomogeneous, but we don't know exactly what it is, and it might be, maybe you can map it back to, I don't know if it's a simple transformation of the KPZ fixed point, or it's something more different than that. So I don't know. It's the sort of thing that we would like to know, that I would like to know.
Thank you.
So related to, I think, related to Avelio's question. So if we have some very local dependency, like in the ballistic model, like your Poisson rate, the way the particles are falling are a little bit dependent in space. Still will be the same class, or can you prove anything?
Okay, so when you, yeah, if maybe I can expand on the answer. So the sort of thing I was thinking when Avelio asked is some sort of what you're saying, some sort of little dependence. Like you should imagine that there's like the density of your Poisson point processes sort of varies. If you look at it macroscopically, it varies smoothly. So in that case, what you should see is that you should see something which is either just the KPZ fixed point or some simple transformation of it or an inhomogeneous version of it, but it will sort of be the KPZ fixed point. Now you're asking, maybe because at the beginning you said, what happens if you have a single site or a single region, you change something? So you can change this macroscopically. So maybe you can, so let me go back now to the example of the cars. So suppose I have a single position. Okay, I have my cars that jump to the right, but maybe there's one piece of the road which is slower. So maybe there's a traffic light at one position. So you have your cars coming, but when they come here, you can model it as they jump, and the jump rate is less than that. So that would be a very local perturbation. And that actually changes. It doesn't quite change the universality class, but you see something different. You can perturb things like that, and you do see different things. And it's not exactly the KPZ fixed point. Now it sort of depends on where you look. If you look very close to this perturbation, you see something different. Usually around here, it's going to be Gaussian because the effect of the fluctuations coming from this, it's too large. So you're back in the central limit theorem. But then when you go far away, you see KPZ again. So yeah, there's some cases which are understood. Not the one that I just said. The one that I just said is not understood.
Thanks.
But that's the sort of thing you can ask. I don't know if I answered your question. But the problem is that in general, if you want to do something like everywhere inhomogeneous, we don't know how to do it. That's the short answer. We don't know.
Some more questions?
Yeah, so then I'll ask another question. So at the end, I'm not sure I follow, but you sort of gave some reason why these random matrices will appear in when you study some other thing, right? Can you explain why this random matrices will be related to this longest increasing sequence problem in the same way, or because it just turns out that the same equation matters?
Okay, I can't go very. So if you want to, okay, so the question was, I'm going to try to translate. Can I translate what I said about the longest increasing subsequence? I don't know. Like I can tell you what's the translation, but it's not really a longest increasing subsequence phenomenon. It's more a phenomenon about this PNG. So yeah. So what I need to do is I need to couple lots of different longest increasing subsequences by doing the following. I have my point process here, and now I really have to move this. So suppose that I move this over here. I'm going to have a rectangle now. Inside that rectangle, again, I have to look at a path going up. And I also define a longest increasing, I also define a random permutation. It's also a uniform random permutation because of scaling invariance. So let's say if I go here, I have another longest increasing subsequence, but they're coupled, right? Because they share some points. Okay. So suppose I do that for every x. So now I have a collection of coupled longest increasing subsequences. I have a collection of coupled permutations. And out of those, I have a collection of longest increasing subsequences. If you give me that freedom with that special coupling, then the length of the longest increasing subsequence with that extra parameter, in the way that I show, asymptotically solves this KP equation. And then by scaling invariance, you get the random matrix distribution. But I can't quite do it just by looking at the single one. Okay, it's not very satisfying. But if you it's very strange when you look at it in terms of the longest increasing subsequence, but it's very natural when you look at it in terms of the growth process. Because what I'm doing is I'm looking at the height over here at every single at different x's, and I'm looking at the equation that this thing solves. And the right solution of that equation gives me back directly the random matrix distribution. Okay? Something like that.
Okay, unless Marco Kiwi have another question, so we can thank our speaker. Thank you, Daniel.
Yes.
We have